So what we had done was for an n input NAND gates, so we had said the logical effort will be n plus 2 by 3. All right, and then the parasitic was n. And similarly for the n input NOR gates, we had said the logical effort is 2n plus 1 by 3, and the parasitic is n. Right. Let's try to validate this results. Validate in the sense the linear delay model. What we had used, why we are using is to estimate the delay p plus gh is equal to the normalized delay. Right. Again, it is p plus gh will be the normalized delay. The absolute delay will be nothing but p plus gh multiplied, the whole multiplied by 3RC. So let's take a quick example here. If I want to have, take a very simple example of a NAND gate. So 2 input NAND gate, right? So I will have the P value as 2, and the G value for this particular NAND gate is, 4 by 3. Now this particular NAND gate is going to another NAND gate for a two input NAND gates again, and this output gets connected to one of the inputs. So what we are interested in, this particular A point to this particular X point. So the delay of this particular first stage. So we are not bothered about the other stage at this particular point of time. So what should be the propagation delay from A to X? And I've written a smaller d here. That means that I'm interested in the normalized delay, right? So using my P plus GH model, the linear delay model, this particular P plus GH model, so I will use for this particular delay, for this particular gate of 2 input NAND gates, I know that the P value, its parasitic delay is nothing but 2, because it's a 2 input NAND gate. G for this particular, the logical effort of this particular, the first stage 2 input NAND gate is 4 by 3, and then H. Again, it's a normalized value. So what should be H here? H is nothing but, so let me pick up a different colored pointer. So this H is nothing but whatever is the load capacitance coming from the next stage, the loaded capacitance coming from this particular stage is nothing but, it's a 2 input NAND gate. So it will give me 2C plus 2C, 4C. Its own parasitic capacitance is nothing but, so if I draw 2 and 2, so that will be 2 from the NMOS side and 2 and 2 from the PMOS side. So it will be 6C. Now just to separate it out, 6C and then 4C. 4C is coming from this particular input of the next stage. So this H value, the electrical effort of the fan out is nothing but whatever is loaded from this second stage, whatever is the load capacitance, which doesn't include its own parasitics. So 6C is not getting involved here in estimating the value of H or the electrical effort, because the electrical effort or the the fan out is basically considers whatever is loaded. Right, it's not its own stage parasitic capacitance. It is the external load capacitance. So that is, coming from the next stage, the input capacitance divided by its own input capacitance. So the own input capacitance is nothing but 4C, because it's an AND gate only. So I will have 4C divided by 4C. Right. So which is nothing but 1. So finally, what I have is the normalized delay from A to X using my linear delay model, which is nothing but P plus GH model, is nothing but 2 plus 4 by 3, right? Turns out to be 3 plus 3 into 2 is 6 plus 4, which is nothing but 10 divided by 3. So this is my normalized delay, right? Hope this is clear. So let's try to validate this using my own capacitance model. I've written the capacitance model here of 6C and then 4C. So the overall delay, although I need to find out the normalized delay. So I'm going to write the overall delay, assuming that the switching resistance here for the charging and for the discharging, whatever it is R, linear delay effort. So R into the 10C capacitance seen at the output node divided by 3RC, which is coming from the inverter delay. So finally, I'll get 10 by 3 here. Right, so this delay is nothing but whatever is the capacitance seen at the output node, which includes the parasitic of 6C, and then the 4C capacitance coming from the next stage, which will be 10C multiplied by R, the switching resistance, either falling or rising, and then divided by 3RC coming from the inverter. So it will be 10 by 3. So this particular value of 10 by 3 matches with that of this 10 by 3. Okay, so our P plus GH model, or whatever, we have generalized the P and the G factor or the G values or the expressions. It eventually should give us or should lead us to the same delay what we'll be calculating otherwise, right? So one more important aspect here to notice here is, because I have cascaded the stages, so while cascading this second stage, I'll use a different color. So this particular second stage, so I'm going to write it as the second stage, and then this is my first stage. So the second stage is going to load some capacitance at the X node, at the output of the first stage, right? While I'm calculating the parasitics P value, the P value, the normalized delay, the P value is by far the definition of the parasitic capacitance seen at the node X, right? So I've consider 6C divided by the inverter's capacitance of 3C. And that's how I have got this 2. Right? So for this particular stage, the parasitics, what I've done, it is 6C divided by 3C and it is equal to 2. Now this 6C is actually coming or drawn from its own parasitics, and we have not included this 4C here. Right? So we have not included the input of the second stage into our calculation of or expression for the parasitic delay. So that is important. So the parasitic delay for the first stage, so P plus GH for the first stage, the P value, how do we calculate this? This is nothing but its own parasitic capacitance 6C divided by the 3C inverters, its own parasitic capacitance, right? Giving the same output current for both the gates, right? So this particular calculation or estimation doesn't include the next stage input capacitance. So that is anyways taken care by the factor of H here, right? So when we do P plus GH, this H value or this particular H value is going to consider the next stage input capacitance, right? So this particular parasitics is its own stage. The first stage or the second stage, whenever we are calculating the delay of the next stage, right? So we'll calculate the P value for the next stage, right? So its own stage parasitics we will estimate. So that will be 6C divided by 3C, that will be 2 for in this particular case, right? So hope this is clear to some extent. Moving forward, what we will see is slightly different circuits, although developed from the CMOS families, but it is called as a tri-state circuits. Right, so what we will do is we will establish the logical effort and then the parasitic delay for a very primitive tri-state circuits, and then from then on we will go on to the little bit more accomplished circuits. So what is a tri-state circuit? Tri-state, as it is defined, it consists of 3 states, right? One is the high state or a low state, and then the last one is called as an high impedance state. Right, so what it also means is nothing but a floating state. So we'll come to it. So this is the schematic representation of the tri-state circuits. Given an A value, given the A input, the Y should be nothing but A if the enable is enabled or activated. Or if the enable is 1, we will have Y is equal to A. If A is equal to 0, we will have Y is equal to 0. If A is equal to 1, I will have Y is equal to 1. Right, that's how this 1 and 0 are covered. Now, what is this high impedance state? If the enable is 0, if it is not activated, or if it is not, if the enable pin is disabled, not enabled at all, the Y input is called as the Z state, which is nothing but a high impedance state. It is also called as a floating state because, if I consider the capacitance here at the Y output, it will either be charged or discharged. It will either be charged to VDD or it will be discharged to 0. It will either be holding a value of logic 1 or logic 0, depending on the previous state. Previous state means whenever the enable was active, whenever the enable was 1, right? Whatever was the input, the output, whatever was the output, it is likely to hold it. So that's why it is called as the floating state, right? And the high impedance is coming because we don't have a connection at the enable side. So it's basically an open circuit. The Y is kind of not connected to the ground or to the VDD, and that's why we say that it is it is having a very high impedance. The floating state is its appropriate definition. So one can easily visualize if it's a floating state, that means that it should carry the previous state, right? When the enable was, previously when the enable was 1, what should be the output Y value, right? In a CMOS circuit representation, the most primitive circuit for a tri-state family will be nothing but tri-state inverter, right? So the tri-state inverter means nothing but I will have the circuits connected like this, where the output Y will be nothing but equal to A bar, right? So whenever the enable is 1, that means, in this particular transistor, this will be on. Enable bar will make this PMOS transistor on when enable is 1. And this output is going to either discharge or charge to VDD or discharge to 0 based on the input A. If input A is 1, this will be on. Input A is 1, then this will be on, and then this will be off. So I will have my output discharge to ground. If input is 0, this will be off, this transistor will be off, and then the PMOS will be on, and then I will have my output charged to VDD, right? When enable is 0 here, that means both these transistors will be off, right? So Y will be disconnected from the transistors which are connected to the A input, right? So when enable is 0, this will be off. Enable is 0, enable bar will be 1, that means the PMOS transistor will be off. Y will be disconnected from the VDD or the ground rail, so it will hold the previous state. Now what should be the logical effort of the input A? Input A is connected to these two transistors, and again by the same definition, if I want the same falling resistance or the rising resistance, I will have this sizes accordingly made, selected. So the size of 2 and 2, because both of them are in series, so I will have a size of 2 and 2, which will give me a falling resistance of R, and the size of 4 and 4 here, which will give me a rising resistance of R. So here a 2 and 2 will give me a falling resistance of R. So my logical effort for the input A is nothing but this particular size 4 and then this particular size 2 divided by 3. So that will be 6 divided by 3, which will be nothing but 2. Normalized parasitic delay GA P value will be nothing but whatever is the capacitance in here. So the capacitance in here is nothing but coming from 4 and 2, so 6C capacitance. So that's why 4 plus 2 divided by 3, which will be nothing but 2. All right. So the logical effort and then the normalized parasitic values, we will use the same definitions. So for the normalized parasitic, it is nothing but the output capacitance, its independent stage, standalone gate, whatever is its output capacitance divided by the inverter, benchmark inverter's output capacitance, giving the same current. So both the gates should give me the same current, output current. So that's why we have selected those sizes appropriately. The logical effort, again, based on the sizes, we have to select the sizes such that it will give me the same output current, and the sum of those sizes on the PMOS and NMOS side, which divided by the 2:1 inverter's input size, will give me the logical effort. All right, so hope that is clear. Moving on, what we really want to see is, tri-state is kind of very, very useful for designing the multiplexer circuits. And one of the reasons is tri-state is very simple to implement. So you will have, you are going to have a mirror topology. So whatever is there implemented on the NMOS side, the same thing gets implemented on the PMOS side. So whatever is implemented on the pull down side gets implemented onto the pull up side. That is one advantage. The second advantage is simplifies the circuit, although the output will always be a complemented output of the input. So in both the sense, and it could be also be the other advantage is it can be easily be constructed from the CMOS circuits, right? So in that sense, the tri-state based circuits are kind of very easy to implement, and multiplexer is one such application where the tri-states are heavily used. But before going into the tri-state multiplexer, let's try to understand the multiplexer output logic expression, right? So what I meant was, so if I want to define the multiplexer, so what it means is I have an input. The basic multiplexer will be 2:1 mux, right? So I have A and B as an output, as an input, and Y should be my output. And I should have a select line here, right? So I can also say that, this is a select pin, S pin. So whenever S is 0, we are saying that Y will be A, right? So it is nothing but the input pin number 0 and 1. And whenever the S is 1, we will get the output as B, right? This is what the basic definition of the multiplexer is. So Y as an expression, I can say that it is nothing but when S is 0, I will get A, and then when S is 1, I will get B. All right, so this is what we want. Going from the tri-state. Hope this is something everyone should be aware of. So a 2-input multiplexer which is made from the tri-state. Tri-state will always give you, tri-state based circuits will always give you a complementary output. So what we are seeing is a Y is nothing but S bar into one input plus S into the other input, what we had seen in the previous slide. Not only that, but it's a complement of it. So I will have a complement bar. So this is the inverted output, right? It's basically an inverted 2:1 mux. So how will we draw this? So we see this as a 2 branch. So S bar and D0 as one one segment, and S into D as the another segment, right? What I meant was segment is, so this particular part of the circuit is going to give me S bar D0, and then this particular part of the circuit is going to give me S D1. Tied together, both of them will give me the complement of it and then plus, right? So let's try to understand the circuits, the design of the circuit. So in this particular part, the input D0 is connected to the transistors, PMOS and NMOS transistors, which are very close to the rails, VDD rails and the ground rails. The select line, S bar is connected to this NMOS, and S is connected to the complement of S bar will be nothing but S is connected to the PMOS. So whenever S is 0, this will be on. S is 0, PMOS on this side will be on, and based on D0, I will get the output here. Okay. And on the other segment, so we have the D1 connected to the PMOS and NMOS transistors, which are closer to the ground and VDD rails. And I have S connected here and S bar connected here. All right. So what it means is if S is equal to 1, here, this will be on, and then S bar will make it 0, and then this will be on. So when S is equal to 1, this branch will be off, right? So this on will go off when S is equal to 1, right? PMOS 1 will be off, and then S bar will be 0, and that will be off, and then this will be on, and then this will be on. So I will get the output Y based on the D1 input, right? When S is 0, I will get, Y is nothing but based on the D0 signal, right? So it is basically Y will be D0 bar or Y will be D1 bar, right? So that's what the output is. So if I connect both the branch outputs, I'll get Y is equal to one of the outputs, right? Now coming to the sizes. So what we are saying is one of this particular branch, right? One of this particular branch will be operative or will be connected to the output, right? So I need to size it accordingly such that I will get Y connected to the VDD or Y connected to the ground, right? So if I take this particular segment, I will have the size of these two transistors as 2 and 2. The reason is, in the worst case condition, this will be off. So this will not have any discharging path. And I will have the discharging path connected only from Y to ground. So I will have a size of 2 and 2, giving the equal falling resistance as R of that of the 2:1 inverter. Similarly, for this particular two sizes, I will have it 4 and 4 so that one of this path will be on and I will get the rising resistance as R. And if I have the sizes as 4 and 4, which will give me a rising resistance of R, and then 2 and 2, which will give me a falling resistance of R, that means I'll get the equal output current, same as that of the 2:1 inverter. And similarly, if we have designed it for this particular branch, we should be able to design it for this branch also. Very, very similar. So I will have 4 and 4 and 2 and 2, so that in a worst case condition, this will be off and then this will be on. And similarly, when this is on, this particular path will be off, right? So I will have a size of 2 and 2 and 4 and 4. So if I have this selected size of 4 and 4 and 2 and 2 on both the branches, at the output side, if I want to find out the parasitic capacitance, I need what is the overall parasitic capacitance seen at the output node Y. Turns out to be nothing but this 4 plus this 4, this 2 and then this 2 will contribute to overall I'll get 6C multiplied by 2, which is nothing but 12C. So the normalized parasitic delay will be nothing but 12C divided by 3C, which will be nothing but 4. This 3C is now our inverters, 2:1 inverters, parasitic capacitance. The logical effort, there are D0 is one input, D1 is another input, S is another, select signal. So if I want to find out the logical effort of D0, it is nothing but its capacitance seen here, which is one coming from the PMOS, another one coming from the NMOS, which will be 6 into C. So this is what 4 plus 2 and then divided by the 2:1 inverters input capacitance, which will be nothing but 2. Logical effort of D1 will be very, very similar, 4 plus 2 divided by 3, which will be nothing but 2. Select line, for the select line, the logical effort is basically the input capacitance seen for both S and S bar. So that's what we take, and then divided by 3C. Right? So in this case, for the select line S and S bar, so I will have 4 plus 2 divided by 3C, it will be nothing but 4. Right? So what we are saying for the select line is, the logical effort for the select line is, we are considering the input capacitance of S, not only S, but also for the S bar. And the reason is very, very simple, is because this S bar will be generated from the S signal somewhere in the circuit, right? Somewhere before the circuit, we will have an S signal directly connected to this particular circuit, this particular module. S bar will be there somewhere generated from an inverter, right? And if we don't know the size of that particular inverter, it's better to take its own sizes here in this module. That's a very conservative approach, and then calculate and estimate this particular G value for estimating the delay, right? So in that sense, we are taking all the input capacitance of not only the S as well as its own complemented input. So I will have S and S bar, so it will be 12C divided by 3C, which will be nothing but 4. So hope this is clear, the logical efforts and the normalized parasitic delay for the 2-input tri-state multiplexer. So continuing further, what should be the 4-input tri-state multiplexer? So if I have 4 input, so we will calculate, so we will have an expression like this, S1, S0, when it is 0, I will have a D0 signal. When 0, 1, for 0, 1 case, it will be D1. For 1, 0 case, it is D2 input, and then 1, 1 case, it is D3 input. So there are 4 inputs, D0, D1, D2, D3, which gets at the output based on the 2-input select lines. So S1 and S0 are the 2-input select lines. So this is the expression. So I will have basically 4 branches, right? So one branch is this, another branch is this, another branch is this, and another branch is this. All right. And this 2 input is going to one NMOS transistor and one PMOS transistor. This D0 is going to one NMOS and one PMOS. So in each branch, I will still have 4 transistors. Again, this 2 input, combined input will go to one NMOS and one PMOS transistors. Of course, its complement will go to the PMOS transistors. Again, complement will go to either PMOS or NMOS. And D1 will go to the transistors PMOS and NMOS transistor, which are closer to the rail. So I'm still imagining or visualizing this as a individual branch as a 4 transistor circuit, 2 transistors on the pull down side and then 2 transistors on the pull up side. And we will have the same sizes because it is still the 4 transistors. So either one of these branches will be on. So I will have the PMOS to NMOS transistor ratios will still be 4:2. So the logical effort of all the input signals D0, D1, D2, D3, and I've not taken the select line logical effort. It's only the input signals D0, D1, D2, D3 will be nothing but 4 plus 2 divided by 3 will be nothing but 2. And the normalized parasitic delay, because I have 4 branches now, so the output node, I will have 4 plus 2 multiplied by 4 because there are 4 branches. So this is the number of branches. And then this 2 plus 4 is coming from the transistor which are closer to the output rail. So it will be the input fed to this particular transistors will be the select lines and its complement. Right, so those are, I will call it as the transistors driven by the select line signal. So it is 2 plus 4 multiplied by 4 divided by 3. 3 is coming from the inverters, benchmark inverter 2:1 benchmark inverters output parasitic capacitance. So it will be 2 plus 4, 6 multiplied by 4 divided by 3. So this will be 8. Right, so if I look into the two input Tristate multiplexer. So if I go back, the parasitics was 4 for a 2 input Tristate multiplexer. And if I come back to this current slide, for a 4 input, it is actually 8. So for an n input Tristate multiplexer, it is nothing but 2 plus 4 multiplied by n for the n input divided by 3. So this 2 and 4 is coming from this select line transistor. And this n is nothing but the n number of branches or the n number of inputs. So which will give me 2n parasitics. Remember that the logical effort still remains 2 here for the inputs. Even in the 2 input Tristate multiplexer, it was still 2. So the logical effort doesn't change for an n input multiplexer if you are designing via the Tristate. So that is a clear-cut advantage. So if I am having a delay P plus DH, this G value, right, for an input doesn't change, right? Whereas the P, of course, it will change linearly with respect to the number of inputs, but this G value doesn't change, right? So if I design it in another way, we will have a change in P, we'll also have a change in G. So in this particular case, when we have it branch-wise, based on the number of inputs, the G value doesn't change. Right, hope this is clear. And just to complete the overall the logical efforts and then the parasitic delay, basically the linear delay model. What I've done here in the next 2 slides, including this one, will be trying to showcase the Elmore delay model based delay estimation. And compare with that of the linear delay model with respect to the number of inputs. So I've taken a simple example of an NAND gates, which is an n input NAND gates. So for an n input NAND gates, I will have n such PMOS transistors and n such NMOS transistors. And I will select the size of n here on the NMOS side because I need an equivalent falling resistance to be R, giving the same output current of I as that of the 2:1 inverter. And on the PMOS side, the sizes should be nothing but 2, right? But it will have n such transistors. So at the output node Y, I will have each of this PMOS transistors contributing a capacitance of 2N, and this NMOS transistor, the closest one to the output rail, the transistor which is closest to the output node, will contribute to NC capacitance. So the overall I'm seeing a 3 NC capacitance, right? Using an Elmore delay method, signifies that I need to account for all the internode diffusion capacitance, NC, NC, and NC, all the intermediate diffusion node capacitance. I need to consider that while estimating the delay, right? So what it means is, for the, I've taken the propagation delay for the falling. That means, for the n input NAND gates, all the n inputs here on the pull down side should be 1, so that the output will discharge to 0. So I have taken 3 NC multiplied by R. So R is nothing but the switching resistance of all this N transistors which are in series will give me a switching resistance of R, equivalent falling resistance as R. So it is 3 NC into R. And then I need to accommodate for this particular capacitance plus this particular capacitance, for N plus this particular capacitance, and so on, right? This one 3 NC is already accommodated here, right? And I'm left with now N minus 1 transistors, starting from starting from this one transistor, then the second transistor, then the third, up till this N minus 1. The N transistors, this particular its own parasitic is anyways accommodated in this 3 NC. Okay, so let me take a different color. So what I've done is I've taken a summation signal, and I is going from 1 to N minus 1 transistors, and its parasitic diffusion intermediate diffusion node capacitance is NC, and its equivalent resistance in this case I am taking it as IR by N. So each of these transistors is showing a resistance of R by N. This transistor, the second transistor, should also give us an R by N, right? But as we are proceeding from down to up, right, closer to this particular transistor of NC, it sees a resistance path of R by N. The next one sees a resistance path of 2R by N. The third one sees an the third NC capacitance sees a resistance path of 3R by N, and that's why I have made it a variable of I, R by N. So if I have written this particular generic expression for the Elmore delay, then further calculating, so this n and this n will get cancelled. R and C are nothing but constants, will come outside, and we have the summation of I ranging from 1 to N minus 1. So this will be nothing but N minus 1 multiplied by N divided by 2. And if I take RC common, so it will be 3N coming from here, and then N minus 1 multiplied by N divided by 2 is coming from this particular expression. So finally, if I resolve this, I'll get N square plus phi N by 2 multiplied by RC. So this is my Elmore delay, propagation delay falling using the Elmore delay method. If I use that particular expression to draw a profile of the propagation delay falling with respect to the number of inputs, so if I keep N is equal to, let's start from a 2-input NAND gate. That's the most primitive NAND gates we have. So for a 2-input NAND gates, I will get N square, which is 2 square plus phi into 2. So that will be 14. 2 square plus phi into 2. So 14 by 2, which will be 7. So this will be nothing but 7 RC, absolute delay. Whereas a linear delay model is going to give me the output node capacitance, or rather, the propagation delay falling will be nothing but whatever is the parasitic capacitance multiplied by the 3 RC. So the parasitic capacitance is nothing but, we know that it will be N, the output node capacitance. Whatever we see at the output node capacitance, so the parasitic capacitance seen at the output node, we ignore the internode diffusion capacitance completely in the linear delay model. So it will be N into RC. So for a 2-input NAND gate, it will start from 2 into 3 RC, which is nothing but 6. Right, for a Elmore delay method, it gives me slightly 1 RC above. So there is a deviation. If I go for it N is equal to 3 input, I know that this value will be 9 RC on the linear delay model. On the Elmore delay method, it turns out to be 12 RC. So this difference which was 1 RC here in the 2-input NAND gate. Now it grows to 3 RC in the 3-input NAND gate. In the 4-input NAND gate, the difference is quite more. In the 5-input NAND gate, the difference is even more, and so on. So the difference between the Elmore delay method, which is more appropriate, and the linear delay model keeps on growing, right? And the linear delay model, what it says is, of course, it's a non-linear delay model. It grows quadratically with the number of inputs. So the n square here, as the n increases, the number of inputs coming to the number of inputs that defines the n input NAND gate, if it keeps on increasing, the Elmore delay method shows that the delay increases quadratically to the number of inputs to the gate. So the advisable is, beyond a certain number of inputs, it is not advisable to have more number of inputs in a gate. So it is advisable to keep that number of inputs to a limit, right? So what is advisable, as given in the textbook, Weston Harris is, you have, if possible, design the circuit till the number of inputs reaches the 5. So beyond 5, if I use a 6-input NAND gate, the difference is very, very huge, right? And if I'm doing a rough calculation by a linear delay n-input NAND gate, the difference is huge. That is one. The second thing is, if I consider the more appropriate model, which is an Elmore delay method, right? If I use a 6-input NAND gate, it will be somewhere here, even beyond that. The delay is actually very, very high. So if I can resolve that, the 6-input NAND gate from, let's say, a 4-input NAND gate or a 3-input NAND gates to such 3-input NAND gates, if I cascade it, if I have, instead of 6 inputs, right, if I can actually do it using 2 such NAND gates, right, and that will be much more preferred, because my delay of 12 RC as compared to quadratically increased 6, it will be very, very high. So instead of that, having a lower 12 RC delay from 1 and then 12 RC delay simultaneously, and then getting it connected to the next stage, right? So it is always advisable to keep the number of inputs connected to the NAND gates or the NOR gates, limited to 5. Right. One thing is, when I have more than the 5 number of inputs, the linear delay model estimation will be completely off. And the second thing is the Elmore delay method, which is more appropriate, but still, as a delay increases quadratically with the number of inputs, it is, even if you use an Elmore delay method, it's going to be very, very high. So why not reduce the number of inputs and then redesign the circuits? So we'll need the same output, right? But by using multiple such NAND gates or multiple such NOR gates, but having a less number of inputs to those gates.